Earlier we have gone through the theoretical part of pulse code modulation. Today let us see how to find the bitrate for any PCM system. The learning object of this video lecture is that the student should be able to determine the sampling frequency if the student knows the input signal which has to be sampled using the Nyquist theorem, and the student should also be able to find the number of bits if quantization level is known, and using these two the student should be able to determine the bit rate and then try to compare with the practical values available in the other books. Then you will find that there will be some mismatch, and let us see why this mismatch occurs. So first of all, we'll start with the block diagram once more. Here we have not used the first block, which is a low pass filter, because it doesn't cut into the picture for the calculation. I am assuming that the input to the sampler is a signal having a maximum frequency component of B hertz, where B is nothing but the maximum modulating frequency. So at the output of the sampler, if you want, you will get the sample which has to be recorded at the receiver side using the filtering, low pass filter. So Nyquist theorem states that you can recover from its sample only if you keep the sampling frequency greater than or equal to 2B samples per second, where here Fs is nothing but the sampling frequency. The next block, square block, which is a combination of quantizer and encoder, you can call it as a ADC with L number of quantization level. Using this L, we can find out the number of bits required per sample. And combination of this, we can find out the bit rate, that is equal to the product of the number of bits per sample and sampling frequency. Here RB is nothing but the bit rate. Let's take a practical example to understand it. That practically this PCM is well known and used in traditional telephony, wherein it's required a speech signal is the input. So speech signal, we know that human audio signal, if someone says, then it is from 20 Hz to 20 kilohertz, but you need not to take 20 kilohertz as a maximum frequency component. Speech signal only we require the intelligibility of the signal, not the fidelity. Hence, practically they take the maximum modulating frequency B equal to 3.4 kilohertz and L equal to 256 kilohertz. The second example of the PCM is used, that is compact disc, wherein audio signal has to be recorded. So in that case, the maximum modulating frequency is taken 20 kilohertz, and the number of level also is kept very high, so that you can get a minute components also, that is 65,530. Now using this data, let's try to calculate the bit rate for the compact disc. Theoretical calculation here we will go through. Our aim is to determine the bit rate from the data provided in the previous slide. So that is nothing but B equal to 20 kilohertz, L equal to 50. From this B, we will go for a Nyquist rate, where we know that sampling frequency should be equal to 2B, so that's 40 kilo samples per second. And from the L, we can calculate the number of bits, which turn around to be 16 bits per second. So hence your total bit rate for the compact disc CD, that is 640 kbps from the theoretical calculation if I take the Nyquist rate. But really speaking, it's never going to be, practically if you see the textbook, it will be around 705.6 kbps. Now the question why it is so? The reason is very simple, that instead of taking that sampling frequency exactly equal to Nyquist rate, they keep greater than the Nyquist rate, that is greater than 2B. And practically they take it around 44.1 kilohertz. Now the question comes back, why they keep greater than 2B? What happens if they equal to 2B? So the practical difficulty is while recovering the signal from the sample at receiver. At the receiver, the low pass filter is generally used to recover the signal from its sample. So if you keep Fs equal to 2B, then an ideal low pass filter is required, then only you can recover the signal. So which is practically difficult to realize, and it may result into infinite delay too. Let's understand it using the spectrum. Here I have shown you three spectrums. The top one is nothing but, I am assuming that the signal is the signal spectrum. You can see here it is band limited to P hertz. Now assume that the signal is sampled. So this is nothing but sampled signal spectrum, and the sampling frequency we have kept 2B. That's why we can see that the gap in the frequency spectrum, the gap between these two, the neighboring. If I keep exactly Fs equal to 2B, then these two will join and this side also they will join. And then if I want to recover the signal, then I should have a filter whose response goes like this, which is nothing but a form of a rect signal in the frequency domain. So in the time domain, it will be a sync pulse and it will not be a causal. So if it's not causal, it is not realizable. So to make it causal, we have to go for an infinite time delay, which is not a practical solution. Hence, the only one way is don't make these two join. So keep the sampling frequency greater than 2V. So you can see they are far apart. Now I can have a filter, realize a filter with some roll-off factor. You can see, and without taking the any component of the neighboring. So this type of filter response will result into some finite time delay. So delay is always going to be present. Because of this fact, they practically they never take sampling frequency equal to 2V, that is Nyquist rate. They always keep greater than 2V. Hence, the theoretical and practical calculations differ in most of the cases. Thank you for attending this.